All right. Hello, hello, hello. Welcome to stream. Welcome. I need to. This music is a little much. Let me try to find something a little bit better for music. Welcome to stream. Hello, y'all. Tonight we're gonna finish the calculus. There's just 2 more problems to do, and then I think I'm gonna do some gaming. Found a game on Roblox. That's a lot of fun. And so yeah, we'll see how that goes. Let me see. This is more like it. Hopefully this is good. Hopefully this stays good. Let's go. All right. So last night, yesterday, last stream, yada yada. We covered a few problems. Number 1, we got number 2 over here. Covering computing integrals. Then we got computing integrals, computing definite integrals using u sub. And then we got finding h prime of x. Using fundamental theorem. Then we got closed interval method. Basically finding an estimation of the value of an integral, or at least where the value is, without actually evaluating an integral. Then we got some volume calculations and all that fun stuff. And yeah, finding intersection points, then setting up the formulas to do the calculations, which is good. And from what I've checked, everything is correct. So oh shoot. Okay. I just realized I actually did not get everything correct. I need to fix on number C, because I forgot to adjust it based on the actual, on making sure it's rotating about the y-axis correctly. Let me pull up the reference notes, and we can fix that real quick. And then we got 2 more problems. One is just calculating particle movement and net distance using net theorem. And then we have an extra credit one that is basically finding the integral as a Riemann sum using definition of an integral essentially. Let me pull that up. This will be under chapter 5. Oh my god. Everything just leads to like EDM. Can I not just get EDM show music? I need to like make my own playlist, I'm sorry. Okay, so this is disk washer method. Okay. Let me get zoomed in to the correct zoom-ish. Let me also set the stylus to be the thinnest pressure. Okay. So this is actually, shoot. This is actually wrong. And so is this. Just barely. Because, let me switch colors. When you're rotating about an axis that's not the X or Y axis, then we want ooh, I don't know if I like that. Okay. It's staying here. Oh my god, let me find different music. This is driving me insane. Why did it switch? No. I want to play a playlist, not the stupid mix crap that Spotify tries to do. Sorry, Spotify sucks. I hate it, but there's nothing better, or at least nothing that's like conveniently better. Okay. So when axis of rotation is not X equals 0 or Y is equal to 0, then we want it to be basically then the cross-sectional area sorry, I'm doing a lot of colons. Then the cross-sectional area is pi. That's a horrible pi. Pi times radius squared of the outer minus basically minus, I guess we're gonna, in this I'm gonna write delta x, basically assuming that is the distance from the axis, or no. I'll say delta y. So change in the rotational height, I guess. Minus fuck. I'm trying to think of how to explain this variable correctly in a way that's more adaptable. Because the reference that my professor gave is kind of just shit. Because it doesn't actually give a formula. Let's see. Do a axis minus r squared inner a of axis, which means that our formula over here is not quite the right one. Because instead of just simply the outer minus the inner, it'd be pi times let me double check this before I write it down. Pi. Oh, my paper's gone. That's okay. So the outer is x. Minus -1. Or no, it's not minus the axis, it's plus. It'll be plus -1. Minus the x cubed plus -1, which simplifies to pi times x minus 1 minus, or no, x squared. Sorry, getting my math brain back. And this is x to the 6th. And it's x squared minus x to the 6th minus 1. And there we have that. And that can be used to say our volume is equal to pi times the integral from 0 to 1 for x squared minus 1 minus x to the 6th minus 1 d of x. And I'm pretty sure that is a more correct answer. And so there we have that. Okay, so we fix that. Let's just go over here and let's start number 7. Number 7 says suppose a particle moves along a straight line with velocity in meters per second of v of t, which is equal to 12 minus 4t over the time interval of 0 to 4, which is the time in seconds. Whoops. Okay. Then we got let me move my hand over. A, which says find the displacement over the interval. Okay. And that's pretty easy because we already have a function. So we can just say we want to find the integral from 0 to 4. Oops. Oh my goodness. Of 12 minus 4t dt, which we can already integrate to be 12t, or to be the integrand of 12t minus 2t squared from 0 to 4. Right? So now we can just solve, which means we have 12 times 4 minus 2 times 4 squared minus 0. which can simplify down into 48 minus 2 times 16, which is equal to 48 minus 32, which is just 16 meters traveled. Okay, so that's pretty easy. That's just definite integral solving. But now for B, we want to find the total, distance traveled. Ooh, my wrist is already cramping. Which is now different because we want to make sure that we are including that distance that is not found by 0. Move down a little bit. So first, we want to find the critical point or points of t, or of our function of velocity. Whoops. That works. Critical points of b of t is equal to d 12 minus 4t. Right? So now we can just say 0 is equal to 12 minus 4t. We'll move it over here. 4t is equal to 12 by just adding on both sides. And then we can divide on both sides to find t is equal to 3. Right? And so now we know that at t equals 3, which is within our interval of 0 to 4, we know that there is a critical point, and so we need to do a test. So let's try v of let's just try v of 0, which is just 12 minus 4 times 0, which is just 12. Whoops. Okay. And we can test v of 4 as well, which is 12 minus 4 times 4, which is equal to 12 minus 16, which is just -4. Pretty easy, straightforward, right? So we know that from 0 to 3, basically from 0 to 3, b of t is positive, and then from 0 or from 3 technically we didn't test at 3, so we don't really know for sure, but it doesn't really matter because we can assume that will be good enough a lot of times, unless it's very specific. And then from 3 to 4, v of t is negative. Not too bad. Okay, so now we can actually start setting up our integral. So we can say that our delta x, so our change in distance. Well, that's not change in distance because that's just displacement. Yeah, I don't know if there's really a variable that I can easily set. But the integrand, or integral, of 12t, or 12 minus 4t, dt, from 0 to 3, is one side, plus the integral of negative 12 minus 4t, dt, from 3 to 4. Right, because we know that from 0 to 3, v of t is positive, and 3 to 4, v of t is negative. So we want to make it, we want to inverse that to make sure that we are getting that total distance in the end. Which means that this is all equal to basically the integrand. I think that's the correct term, is to say integrand when you're actually doing it. But I'm going to say it because it makes sense to me. And if I'm wrong, then say so in chat, please. The integrand of 12t, so like before, minus, not 4, 2t squared from 0 to 3, plus the integrand of negative 12t plus 4t, not 4t, 2t squared from 3 to 4. So now we just solve. So this first one is kind of easy because it's pretty similar to what we had initially. 12 times 3 minus 2 times 3 squared minus 0 plus, then we have negative 12 times 4 plus 2 times 4 squared minus negative 12 times 3 minus or plus 2 times 3 squared is going to be like a lurk ominously. Yes. Well, hello, Jeff C. Grooves. I think I'm reading that right. The text on my little preview screen is small. I apologize. I don't really have chat commands. I don't have a lot of time to set that stuff up yet. Hello, do you do math on stream? I do on occasion. Right now I'm just doing math homework. And then sometimes I'll do math. Like right now, because of college. A lot of math homework. Well, thank you for the follow. Yeah, I could do more math on stream. Do you take questions from the audience? I can. Let me finish this up, and I can. Well, actually, let me write it down. I can write it down real quick. Shoot, this is the laggiest thing possible. But yeah, I can write it down and get to it in a moment. What you got? Oh, I was asking in general. I can. I'd happily do so. I'm just trying to finish this because this is from some of my assignments that I'm just working through. Sorry, a little scatterbrained tonight. It's been a long day. All right. Well, I'll get through this real quick. This is just calculating, so do anything about spherical polygons and Voronoi diagrams. Not off the top of my head, but I could probably look it up and try to work through it. If you got a problem that you want me to work through. So I have read a lot of magical math stuff from my time in programming graphic stuff. But yeah. So we got 36 minus 2 times 9. Minus 0. Sample problem, find which points in the world are closer to France than the USA and vice versa, where both nations are considered sets of spherical polygons. I know the answer is based on a parabola, because just how flight paths are. Which points in the world are closer to France than the USA and vice versa? Yeah. Yeah. For polygons that are, yeah. I would imagine so. Final points in the world. That are closer to France than the USA and vice versa, where both nations are considered sets of spherical polygons. I'm curious. I'll look into that. Let me finish going through just writing down this stuff. You got me intrigued. All right, so then we got negative 48. Oh, that is a shitty 48. Plus 2 times 16. I don't have like a proper glove for the drawing tablet I have that I'm borrowing. So my writing's a little funky sometimes, and I apologize for that. Okay. All right. Well, I'll check it out in a second then. We'll see how this goes. Plus 2 times 9. So we got that, which is equal to 36 minus 18. Plus negative 48 plus 32 minus negative 36 plus 18. Don't be doing that. Come on. So we got 18 plus negative 16 minus, or I guess plus 18, which is equal to just 18 plus 2. which is equal to a total of 20 meters. And there we go. And we got that. Oof. My wrist's not happy with me. Okay. So now that is finding distance traveled by velocity using integral. Fun. I like those problems. Those problems are easy, but they're fun. Alrighty. So now that's all I have for that. So let's looky here. Let's see. Hopefully it doesn't open up a virus. I trust you. I trust you. Okay. Ooh. Oh, yeah, that goes into repeating mode. Okay. It shows the general idea. Yeah. So I like the name. The name of the repo is pretty funny. Geo-winking is funny. All right, so let's see. We got basically there's a Reddit sub. Oof. Oh, it's a Reddit based thing? That's funny. I don't really look at Reddit very much, so but that's funny. Oh my gosh. Okay, it's just being funky. Okay. So this is just finding all of the points that are like closer to a certain state. And so each color relates to a state. So like the yellow is the Texas. Yeah. Okay. Okay. That makes sense. Huh. That is, yeah. Yeah, it does kind of blend to be pretty much the same shades. It's funny. But no, I think I get the idea. Oh man, I have not looked at math like this before. So it's time to do some funkies. All right, I'm gonna create a new board. Oh, that's bright. I'm sorry. New board. Shut up. Format. Go, please. Please, dark mode. Okay. I use Grass GIS to generate that. Okay. So let's see. Grass GIS. Okay. That's funny. Let's see. Raster vector and geospatial processing. Okay. QGIS, GIS. I have not actually. I have not done a lot of projects that deal with like geographic data. My main coding projects that I've been working on is a game engine. Oh, sorry, sniffles. I haven't done a lot of geographic stuff. Let's see. See if I can. All right. Only elegance is that the Earth is a spherical surface and can't actually be mapped to 2D dimensions. I know. That is the sad part. You basically can't unless you make a lot of assumptions. Because like you can technically just UV unwrap the Earth. Yeah, and so you have to distort it, and that's kind of why like no maps are actually considered accurate. I know. Um. Da, da, da. I know. Yeah. I know Greenland is like way bigger on most maps than it actually is. I do know about that. So let's see. Let's paste this down. Ugh, let me get this to a color that's actually like seeable. Okay, that's a little bit better. All right. Let's look at spherical polygons. Yeah. Okay. This is like seen things like this before. Mostly in geometric stuff. Yeah. Okay. Both nations are considered sets of spherical polygons. The polygons defining the countries are at there? Okay. Oof. Maps. All right. F. France. Okay. Okay. So it just kind of matches everything to be like a Vroni patterned polygon. That's interesting. Yeah. Okay. So this is the actual data. So you actually use like this data? Yeah. The actual data, not the map. Okay. Yeah. The coordinate reference system is longitude, latitude. Yeah, the shapefile. Okay. Why did it select like something that I did not select at all? Okay. Oof. That is a lot messier. Where's your danger? All right. So we have a shape file. Oof. That's a lot of data. All right. I don't actually have software that's, for now, I'm using just in the whole country as a polygon. It's not breaking down by province or country. Yeah. I'd imagine so. You don't really want to go by state or province and all that. Okay. Yeah. No, it's a special thing. Yeah, exactly. That's interesting. See how this helpful? Maybe. Close geometric figure on the surface of a sphere. All right. Which is formed by the arcs of great circles. The spherical polygon is a generalization of the spherical triangle. If theta is the sum of the radian angles of a spherical polygon on a sphere of radius r, then the area is s is equal to theta minus n minus 2 pi r squared. Okay. Let me see if I can get Desmos or GeoGebra to help visualize this. Ugh. No, stay on top, please. E. Oh, my watch is buzzing at me. All right. So we go to 3D. I don't care. All right. Yeah. The spherical polygon. Unit sphere? Okay, let me, right, because it's x squared plus y squared, it's a circle, and then you want to, that's right, equal to 1. There we go. Okay, yeah, because that's the unit sphere. I don't know why it had to be difficult like that. Desmos is still a little funky when it comes to yeah. So that's a unit sphere. And the polygon is a polygon that represents an area of the surface of the sphere. Right. I think I've seen these. I haven't really used them before. So let's see how this goes. Let's see if this is any useful. Projection will be from the center of the sphere, since each side of a spherical triangle is contained central plane. The projection of each side onto a transit plane is a line. We will also assume the radius of the sphere is 1. Yeah. Yeah, great circle arcs. Okay. Right. Basically just drawing the longitude and latitude lines, I think, is kind of what it would relate to. Gray circle becomes a straight line in a mnemonic projection. X squared plus y squared. It's not super trivial. Yeah, I mean, it's they never are when it comes to like geometry and complex shapes like this. Yeah. Let's say this is equal to z, or no. We'll do r, and r is equal to 1. Oh, shut up, Desmos. You can figure it out. You're drawing it. Sort of arc is interlined along the x and y and z axis, but the generic great circle can be hard to draw. Yeah, that is, especially when you're trying to project it onto like a generic map. It is a lot easier when you're looking at an actual circle, which I hope that has enough contrast. Let me put this in present mode. I think I can do that. Do they not have present mode in this yet? No. Okay. Yeah. All right, yeah. Yep. Yeah, we don't care about that. Right, because great circle would just be that it is essentially just a subdivision of the Earth that relates to coordinates, and I forget the way that they uniformed it. Can I do something like this? No, maybe. Of course not. Extra will divides Earth into 2 hemispheres, yeah. Yeah. I mean, I might be talking out of my ass, but isn't it that every line of longitude and latitude is technically a great circle because it relates to an absolute radius, or not an absolute radius, but like an absolute diameter? Well, not latitude, right? Yeah, only the longitude lines, because those are actual radius. Yeah. Yeah, and the great circle is the equator. Okay. Because all the other ones are technically just subdivisions. The shortest path between 2 points on a sphere, also known as the orthodrome, is a segment of a great circle. To find the great circle distance between 2 points located at latitude and longitude on a sphere of a radius a, convert spherical coordinates to Cartesian coordinates using the matrix formula. I think that is. Excuse me. Okay. Let's get that up there. Sure, let's do this. Okay. All right, so we have now the shortest path between two points is a segment of a great circle. Cool. Mm-hmm. We want to convert spherical coordinates to Cartesian. Ooh. Is equal to a cosine of lambda I times the cosine of, oh fuck, I forget the name of this variable. Isn't it? It's not omega, is it? I don't know. Yeah, a is 1 in the unit sphere. Oh right. Yeah. 'Cause I know this one is lambda. I forget it. I think it might be phi on the second one. I don't remember. It's okay. That's not super important. That's just variables. Yep, exactly. And then sine. There. Let's see. I want to look up phi. Not phi. Phi. Ah, right. Okay. Fair enough. A little bit bigger? Yes. Oh, get that out of the way. Sorry about that. It's hard for me to tell on that because my little screen is like a little 7-inch screen that I have my preview on. So I do not see a little bigger. All right. 140. There we go. Now it's a little bit. Now it's actually like filling in the page. Hopefully that's more readable. And I can zoom in on this. Lambda and delta. There we go. That's, yeah. Okay. That's what it is. Because, right, because then this is uppercase and that's lowercase. Latitude is 90 minus delta? Okay. Okay. Right, yeah. So it's the co-latitude. So it's just 90 minus that. Yeah, it's all just variables, and it's whoever thinks their convention is right. And so it's oftentimes more, rather than a argument of one variable is better, it's more of an argument of, oh, the way I say it is better. Okay. Mm-hmm. Now we want to find angle, which is dot product. Mm-hmm. All right, so cosine theta. Oh, struggle with the theta on the tablet. Is equal to the dot product of points R1 and R2. Okay. Which is just equal to cosine. Yep, and the arc cosine is therefore the distance. Yeah. Okay. So then, yeah, then it's cosine of that one times the cosine of the second point times the cosine of lambda 1 minus lambda 2 plus the sine, excuse me, ugh. School dinner did not agree with me tonight as much. I apologize for that. Okay, I'm just gonna copy the more simplified version. Less writing. Cause then, oh, whoops. The Habersign formula. Yeah, I know. It seems like they do some kind of simplification here. That's probably based on a formula or some kind of calculus thing that, or trig thing that it's just known amongst the math people that do math all the time. And then we have distance, which is just the a, or the radius, times the inverse cosine of that. Okay. And I'm going to note this down as well, because it says the Earth radius. Yeah, a point is definitely too slow. I see that. So it's figuring out. The real problem is how to make it so it's an efficient algorithm. Basically. Yeah. Okay. Yeah, because we're trying to find what we are doing and its effects. I'll make this so that A is equal to 1. A is equal to something, unless it's just not carrying. It's not carrying. Desmos is funky. I think I have to use GeoGebra, so kill it. No, that's not the right one. I want the 3D one. .3D calculator. Maybe? Possibly. Alright, so we got the x squared plus the y squared plus the z squared is equal to A. And A in our case is 6,708 kilometers. Oops. I don't think we want to do that. I'll reset it to just 1. So that we can at least see it. How we the math going? It's going. We're on a rabbit hole adventure. All right. Okay. Now a radius would be just the x squared plus the y squared, which is equal to, say, 1. I don't know why it does it as a cylinder in this one, but oh man. Okay, you have to specify z equals 0. Plus 0z squared. I don't know. GeoGebra's funky. I haven't used it in a long time. Yeah, that just gives me the plain. Hmm. Yeah. Which, I mean, in this case, I am assuming that it is z is equal to 0 because I'm just doing a 2D plane circle equation here, and it's and GeoGebra being not very helpful. This is why I don't like graphing things. Okay. But overall, we have our circle. And basically, oof. One moment. There we go. Okay. Okay. Yeah, thank you. Tis the season of sniffles. Yeah, so essentially what we're being given is that France is some kind of funky mess of a polygon. Say over here. This is not to scale. And then we have the US somewhere over here. Does something. Oh, I took a screenshot. On Windows, if you do Windows Shift S, multiple polygons for each. Okay. Well, yeah. So it has like different subdivisions, and it's made of different parts. That is right. It is somewhere over the fuck here. I don't know. Oh, multiple disconnected polygons. Oh, so it's like, okay. Let me see. Get out of here. So you got like one polygon. I don't know if this is very viewable against the red. A Corsica. Yeah, it has like a little tiny island somewhere. Yeah. I am very bad at geography. Okay, but it's like multiple polygons, as in it's just like just a bunch of shapes that are, yeah, okay. Yeah, okay. Well, yeah, Hawaii is like however many different, it's a bunch of different islands, and then it also has like Alaska technically that's like up here. Yeah. Okay. I get it. Yeah. 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 I mean, I'm not gonna be able to. Yeah, I know, right? It has a whole bunch of tiny islands and all that. I'm not gonna get that accurately on Windows whiteboard. Okay, but that makes sense. Yeah. We're kind of just given a bunch of polygons that relate to data and mean something. But overall, they all are like, yeah, it's just a bunch of polygons that form a country. Yada yada. Yeah. Yeah, it could be like an estimation of. We could estimate it as just being like some shape like that. And same with the US being primarily just like, oh yeah, it does weird stuff. And then it just has all of its islands separately, respectively. Okay. Because now what we're trying to find is basically what is the, yeah, because like the brute force way is definitely, don't include provinces and stuff, it's just disconnect polygons. Yeah, I mean that's in terms of data. I'm just talking like overall what was the problem, and we're trying to figure out basically what's this middle point here. I don't know if that's very viewable. Is that? No, probably not. Come on. No, that's not even like viewable. Ugh. Green. Let's go lime green. Basically, the brute force method is to calculate an arc and find the middle point, right? And you just have to do that for like every polygon. Yeah, because then you get an estimation of like, oh, you got a point here, 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 so on. And so then you can connect that, and that's your splitting point. Yeah. So it's how do we make assumptions to simplify this, or yeah, the raster approach. Yeah. I mean, hey, you can always GPU compute it. And they'll figure it out. That's a joke. Don't try to do that, especially with a web page. It's not worth it. Yeah. Because they'll figure it out pretty quick. Because it's just a few million operations. Okay. Brings it down to about 1 kilometer. That's pretty good, actually. Yeah. Huh. So it looks choppy. Yeah, I'd imagine so, because it's. Well, I mean, can't you technically? Huh. I'm just trying to think of like as an algorithm, what you want to do. Lines respond to that vector. Yeah. Yeah. Oh yeah, I can imagine. I'm just trying to think of what you can do, because you could let me, oh, that's gonna blend in. Okay, I'm gonna shrink this a little bit so I can see my marker. Yeah, that works. That's enough contrast. If it would undo it. Okay. What we can do is you can basically make, so we have, oh shoot, where'd it go? Come on, come up. I want that, yes. So we have the world, right? And when you look at it, can I don't know if I can really make these brighter. Let's see, Google Maps. All right. No, I need to go to Google Earth. Oh man, why did they make it so complicated? I just want to look at the fucking Earth. That one. Launch Earth. No. Where can I just view it? No, I don't want to do that. There we go. All right. Reset that so I can actually see some of these things. Dismiss. I don't care. Here. Basically, you got some kind of polygon. That just does whatever to shape the Earth, or shape the stupid US, whatever. Close it. Okay, never mind. Where is like any of the useful things? View, grid lines. There we go. There we go. That's what I wanted. All right. So we kind of already have, okay. When you look at the Earth in terms of data, right? We can actually say that the Earth is just a grid. Where the fuck did I put the pen? Over here. Oh, fuck. I didn't mean to do that. No. Right. Because it's a grid, and so it has... That's horrible, but that's okay. I'm not going to school for art. Some kind of grid. Yeah, not Euclidean. But what you can do with this grid is you can actually take it. Oh, I'm sorry. I'm not good at drawing on 3D shapes. You can take it, and because you got, you know, X amount of subdivisions, you can take it and you can say, hey, we have, rather than measuring like the exact distance, you can mark a grid as whether it's closer to France or whether it's closer to the US, right? Because then you can go in and you can say, okay, this one contains part of the US. This one is closer to the US. Well, like, you could, what you could do is basically do a walking algorithm where you are going from the actual like country, right? So wherever the polygon country is, that grid. Okay, let me see if I can. I'm gonna close this and I'm gonna just draw it out over here in a 2D format, just to try to give an example. Yeah. Yeah. Oof. All right. I don't think I need this on top. Sorry if the Windows sounds is loud. Yes. Pretty much this. Because now you have a grid, right? So now you're doing this. And so now everything is formatted in a grid, which is way faster to look through because it's based on quote unquote square. Projection wise, it's not right, but it's a lot easier data wise to keep track of. Because now if I take a screenshot of this. Oh shit, wrong button. Yeah, well, I mean, we're converting between coordinates. If you use it based on the actual longitude and latitude coordinates, I don't think it's going to be as choppy. Let me paste this in here. Fuck. Come on, paste. So now, say we want to find based on the US, right? And it's however the grid will actually look when in data, because this is just a visualization, right? It's not going to be accurate because technically this is curved and this is slightly curved, and this will be slightly curved, right? So it's not, the visualization is not accurate and it looks more choppy because it's trying to adjust to that. But essentially we will have it's just the center of tile at the moment. Yeah, exactly. So basically you'll have, you know, some amount of grid points that's going to be around the US, and then there's also like the Hawaii over here, and then there's the Alaska up there, right? Those grids contain the US, and so we can say, you know, to whatever definition that you want at some point, these contain it and are closer to the US, right? And so now you walk out to some extent, and I don't know which one's France is in. It's somewhere over here. Isn't it? I think it's this one. I don't know. I'm not good at geometry. Not geometry, geography. So we got France over here, right? And so we know that France is, yeah, that's France. Okay, I guess right. So we have France here. So now we can just walk over here and say, okay, this one's definitely closer. And then this one's definitely closer. But then when you get to where Let me try to find a different color. Oh, that one's all beefed up. Let me replace this with purple so it's a little bit more visible. Yeah. And so now we're just walking between each, right? Because now it's somewhere over here. And you can say, okay, this one's still closer to the US. Yeah. So if you want down to pixel level, what you do is at some point you're going to find, depending on how you implement the algorithm, you're going to find these squares that are intersecting, right? So we have these two that are colliding. And so now what you can do is you subdivide it, or you can do the actual math. So you can subdivide it, and then, because now you can just mark, okay, this is all France, but then these are the US. I can't see the mouse. Oh my goodness, is it too small? I'm sorry. Let me. I don't know if I have a highlighter. Might as well zoom in though. Yeah. Come on. Why are you being stupid? There we go. Yeah, okay. Sorry about that. Because now we have this intersecting line, and we're finding that without actually having to do the math. And so now you only need to do the math when you want the pixel perfect point, which you've already done half of the work to where theoretically it's going to be way faster. Because now you can make assumptions because you already have, say, this line, which is a longitude of some amount. Yeah. So do you know, this is kind of like a pathfinding algorithm where we are, well, okay. It's not quite pathfinding specific because it's very broad of an algorithm. But what we're doing is we're generalizing. Basically, we are taking a shape, right? We're taking a shape at some amount, at some size. So what you do is you basically can go, so say this is France, right? So this is France or any kind of other thing. And so now what you can do is you say, okay, this is the equal amount of distance. So this is a unit of distance. Where you can say this is, 100 kilometers or something. Yeah, so you basically grow by cells because now this is step 1. And then you go over here, and this would be step 2, which you go over here, and then step 3. Exactly. So you grow by cells because now if you have, say, the US over here, now you have one over here, and then 2, and then you can do 3, right? So now you're just growing it, and each iteration, You're growing it one more. And so you can do like that. Then you can do like that. And you're just going around basically claiming everything until you hit a collision, right? So now you get to a collision that is on this line. Yeah, basically. And so until you collide, you can do large squares. And then once you collide, you take it and you basically just subdivide it. So you just get a set of smaller squares. And then you actually start doing math. And you're basically reducing the amount of area that you have to do the math from. Oh. Back off on the claim. Yeah. I mean, that's theoretically what the algorithm is trying to do, is it reduces the amount of operations you have to do because you are making the assumption that you can just go until you hit each other. Yeah. Because now, in terms of coordinates, you know that, say, this is, you know that this is what, like, is this, okay, it's F4. Yeah, grab big chunks first, and then you reduce it, and you already know that, say, this line that is going along here, right, is at a longitude of 110 degrees. And so now you already have coordinates to where you're doing a lot less work. And it only gets complicated when you have it to where it has a collision at a corner, which now you basically are calculating it like it's a line between the two. Until you get to the resolution that you are happy with. If that makes sense. Hopefully that makes sense. Yeah. And theoretically, that would be a lot faster because now you're reducing the scale of your math. So you can do smaller calculations, which is a lot faster because you're decreasing the work. Yes, because that means that basically it means that for based on the number of tiles that you're starting from, so like if you had if you added a tile over here to say like China, right, and it grew from here, it's going to add more work, but it's also going to start with large chunks of pixels, but then it's going to grow, and it's not going to, it's just going to add more work because there's going to be a line somewhere in here. Like there's a line over here. And that would theoretically be faster than just calculating that line pixel by pixel, because you're narrowing the scope that it is in. Yeah, exactly. Hopefully that all makes sense. I don't know if I can like give you the, yeah, of course. I don't know if I can give you like the actual implementation, because it's a big project to get started on myself. But I hope that like makes sense in this way that is kind of straightforward to do. All right, that's great. Yeah. Mm-hmm. Exactly. Until you reach a collision, and then you're actually, yeah, and then you just calculate the conflicts. And it's a lot easier when you're working at a scale of, oh, you're working at like 100 pixels or something like that, or 200 pixels. Yes. And so now you can just calculate along that. It's way faster. Yeah. I think that's because now you're not having to calculate a whole distance, and then you're not, and it reduces the areas where you're calculating a radius like across the globe. And it also eliminates calculating if you're like calculating based on the edge of a country or like a given polygon to another polygon. It makes it so that you're not calculating like across the country itself. And so that also possibly, I don't know for sure. It's still, I think it might be linear now. Yeah. No. Maybe. I know it's definitely not as bad. I don't know the time notation off the top of my head for this, just because I haven't looked at like implementations. Yes. Yeah, because you have NN, and then for each operation, no, I think it's still O of n squared, but it cuts out a lot of the wasted performance. Because you're still having to iterate. Each country is still iterating to basically expand it. And then in a collision, in a collision, you're still doing n number of pixels. And so, yeah, but with a lower constant, a much lower constant. And so, because I don't know if you really can do it linearly without just like knowing, oh, we're going to calculate the distance between these two and then find the midpoint, but then we're only going to do that for the area that we know. And you don't really know that, which is what the expanding by a constant rate is what it's solving, is it's reducing the unknown. You're reducing your unknown until you have a known situation to calculate with, which is a lot easier. Yes. Bigger squares means you have fewer squares, and you could do a thing where you do when you reach a conflict, you can like reduce the resolution to where this would be like complex and might not be worth it, because it might just add more work overall. But you technically can reduce the squares to where in the conflicts you can be like, okay, I'm going to split these over these up, and I'm going to figure out, okay, these all belong on that side, these all belong on that side, all the way over here, and these are all over here. And then you can like split it for like a certain resolution. But that's a lot of work to implement. Yeah, it reduces your undecided, which in some cases that's a lot faster. Because technically you could do that until you get to the final resolution. But then you're getting like a notation. Yeah, then you're getting into a time notation that can get really messy if it's like a really bad case. Yeah, exactly. And so really you can do like 2 steps down as your maximum, and it might make it faster. Yeah. Exactly. But say if you're doing like large squares of 100 kilometers, like 100 pixels, you can then step down to like 50 pixels and then 25 pixels, and then calculate once you reach 25 the actual line, and it might be a lot better, but that's really up to testing and implementation, because it might still have time notation problems in the worst case possible. Yeah. Yeah. Well, thank you for asking. It was great. It's a great tangent to go on. Enjoy that a lot. It's fun. It's a fun problem. And I've been, we've almost gotten to that point in my game engine project, where we're gonna have to start working on like pathfinding AIs and stuff to like have pre-built pathfinding. Well, we're not almost at that point, but it's like we can see it in the future, having to do pathfinding, which this is like technically a valid pathfinding algorithm, essentially. But it's not considered the best when you're specifically looking for pathfinding. I forget the name of the algorithm. Let's close some of these things down. Leave, yeah. Shoot. Let's see. Trying to think of what it is. Bellman, Ford. Not quite, because this is based on a node graph. You could use Bellman Ford when you're calculating actual points if you wanted, because you're gonna yeah, it's trying to think. The 2D it's called like a hash something. Fuck. You can implement it with a node graph. I think what it's usually using is some kind of, I forget what it's called. Semantic triples. Not quite. I know that this is what I'm trying to remember, because I remember seeing it somewhere, and I forget what it's called, and it's like a really interesting it's like generally used for pathfinding, but it's also really useful for just like terrain generation and like a lot of other systems. Ugh. 2D map. See if I can just get anything. Let's see. Mm-hmm. Hmm. Nope, not quite that. Oh man, I feel like I'm laying it down, not remembering this off the top of my head. Oh man. Let's see. Nope. Awesome maps. Here, let me check something. I might magically have it in a YouTube folder somewhere. Is this what it is? It's something similar to a spatial hash grid. Oof. Yes, spatial hash grids. Is kind of what the idea is based off of. It's what like the data is based on. I don't remember what the algorithm is called though. For like actually walking through the spatial grid. Yeah. It's basically you're generating a spatial hash grid. So it's just a hash grid without actually doing like object detection. You can use it for that. Man, I'm sorry. I don't remember it off the top of my head. I'll have to find it at some point. But overall, the idea is you format your data into a grid system. And then you can walk through your grid. You can use that grid however you want. And in this case, we're doing a pathfinding search, essentially. And then we are submapping the collisions. See if there's some labels for ones that are just obvious. I think you could definitely say it's similar to like the Dijkstra algorithm and like the what's his name? Bellman Ford algorithms. So your keys basically you're creating a grid where each key is just like the coordinate. And then your grid is like a set amount of dimension. And then it's like it's basically building a tree in a grid. That's what it is. Ugh. Let's see. Let's see. Let's Desmos with it. All right. I think that's trying to make a constant hash based on attaching it based on like the great circle it's on. That's what it looks like. So you could hash it basically based on the longitude and latitude coordinates or whatever coordinate system you're using your data in, where your key is essentially just the upper leftmost corner of that square or something. And then with that, if you want to do like subdivision processing, then basically it's just you're creating a child map. I think this is often it's a hash map that's often implemented as a tree or like a hash map that has like tree capabilities where it can have child nodes. Which is then you just split it into like 4 chunks, and then that is your children to a node. I know it's commonly used in like ray tracing. Yes, whose values can be a hash map itself, so that then you can say, okay, I want to create a child map that is 4 squares that is within the larger like parent square. And then it kind of just, because then you can reduce your resolution. I know it's often used in like ray tracing. Spatial. Yeah, exactly. See if I can find an example image here. Because with ray tracing, what can happen is if you're sending rays from a camera, right? And you want to make sure that you're not like redoing calculations when you don't need to. And so what you do is you make like a 3D rectangle or like primitive shape. So oftentimes a rectangle or a square. And then if the ray hits that square, then it makes a subdivision child node that goes deeper until it gets to where on like a mesh to be able to reduce the number of points it has to check. I wish I could. I don't know why there's not like an easy image example. It's never convenient. There it is. So you could do something like this. It's
hey guys, this is
neural. Mm-hmm. See if we can get this to. Yeah. Because, like, a lot of times in ray tracing. Oh, man. I know there's something somewhere. A lot of times in ray tracing, you want to basically make the world represented in just a giant set of cubes, 3D cubes, that a mesh lives within a set of cubes. And so then if a ray hits one of those cubes, then you do a subdivision to that cube until you figure out what vertex or face the ray hits, to be able to do like the actual light calculations based on that face. So you're kind of just doing a 2D version of that, that is wrapped onto a 3D space. But yeah, I think that's yeah, I can't remember algorithms off the top of my head. I haven't taken algorithms class yet. That's next fall for me, is my algorithms class. Oops. Mm-hmm. Yeah. Mm-hmm. Yeah. Hopefully that'll make sense. I'd love to know. I'll have to keep a record of that. Keep an eye on that project. Yeah. Great. I am glad I could help. That is great to be a help. But yeah. I think I'm going to game for the last hour of stream. After using brain for a long time. That was 2 hours of brain time. I have other homework to do after stream, so I'm gonna game for a bit. We're gonna play some World War II sim on Roblox, I think. I'm gonna take over. Yeah, absolutely. And all sorry for that Windows notification. I'm on Monday, Tuesday, Friday. Same time, 7 to 10, so I might be doing some more math and other things on stream, but yeah, otherwise I do game development, game engine development. So, but yeah, it's glad to be of help, and thank you for joining. It's gaming time, Pacific time, yeah. Just because that's kind of when I'm free from school ish. Mondays, Tuesdays, and Fridays. Wednesdays I have club meetings and stuff, so. Yeah, well, thank you, and have a good night. The sniffles. Yeah, absolutely. Glad to help. That was fun. It's now time to possibly listen to people scream. Ooh, a little bright. Him. BB Alexis, thank you for the follow. I'm sorry I didn't see that earlier. I got hit. Hopefully this is a... Come on. Alright, it's not too bad. Let's see. I got surrounded. There's like no medics in this lobby. Yep, I'm expecting that. I got annihilated. That sucks. All back. I was expecting. Damn. Yeah. We lost. That's not a good match to come into. The allies never win. No. I'll take it. I'll take a random. Hell yeah. Good map. Good sniping map. All right, let's do some loadout work then. Barrel. Damn. Reduce fall damage. Veteran. Yes. I'm gonna remove this sling so I can have a perk. Great. I don't know if I need that yet. Where is the nearest tower that I can get into? And where is the entrance for the said tower? Okay. I always like to play recon. This is fun. Does not seem like people were the smartest in this one. Ow, ow. Oh my god. He nailed me. That's crazy. Oh, bless me, I'm sorry. Damn, almost got him. Oh my goodness. I'm not doing well on this. Okay, that's one. Ow. Oh, man, he can hit pretty well. I don't even know how he's hitting that through that because I can't see him. team. Where be the people at? Yeah, I don't see nobody from down here. And go up a level. And go up 2 levels. I can get height advantage on some of these people. Done. Done for. Oh, the other team just kind of like cut itself in half. Come on, let's get some action. Let's go. Let's go. We're going. We're going. Yum. How are we losing B? Alright, where the hell is the door? Let me out. Come on. Into the church. Oh, gotta build to get up there? Never mind. We don't do none of that around here. asshole. Okay. Zoink tubes. That's wild. Alright, I'm going for a shock trooper. This is gonna be fun. Time to go on the hunt. Got him. All right, got him. That's great. That's great. Oops. So far. Such a far spawn. Let's see. Yeah, he's going. Oh, he got that peak. He got the peak. That is not good. Oh, Heim, bleh. I don't remember the name. Heim something. Are they down below? God darn it. They are. They are just camping down below. And they rushed us. Nice. Nobody's up there. Mm-hmm. 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 Hmm. I'm about to get like yeeted. No. Let's see. Get that heavy ammo and blow some more shit up. Yippee. Let's see, can I get any more? Fuck. I forgot I don't have a pistol. Alright. Oh, we won. Yippee. So nice. This one's a fun map. All right, recon. Oh yeah. Let's see, what can I build here? Let's see, where are the people at now? Nice. Got my own little hideout now. Nice. Shit, I got shot. I ain't getting revived. It's probably the last round for the night, but shit, I got murked because I just ran for it. Bruh. Ugh. Okay, done. Come on, we gotta push him out of here. Mm-hmm. Got him. Haha. Aw, damn it. Okay. Alright, I need to not be recon because it's not a recon mission, it seems. I don't like that. Fuck. No, let's get him. I just need to go gunner mode and then like get on top. Ooh. Excuse me. Squeeze on me. Fuck. Why is there a sniper in the building we own? Or control. There we go. Oh my gosh. How do we just let this guy go in there and destroy us all? Like, we're not losing. It's just the fact that, like, the team sucks. Who put a barbed wire in the bush? Ooh, put a snake in my boot. Let's see, where are you? Hopefully that didn't just backfire. No. Not completely. Nice, we won. Yippee. They even like get past the first stage. Alright, that's what I've got for today. I'm out of juice. It's time for homework and bed. So thank you all so much for joining. Hope you all had a lovely night. Hope you had fun. And yeah, I'll see you on Friday. Bye-bye.